I would like to invite the next presentation by Mr. Yuebao Lei. Please.
Good afternoon, Chairman and ladies and gentlemen. My name is Yuebao Lei from EDF Energy UK. And my topic of this prediction of this presentation is a local limit law model for J prediction while the reference trace measure. First, I'll give an introduction. I try to use the introduction. I try to give the relationship between structure integrity assessment, geometrical prediction, and the limit load. So try to give the relationship. Then answer the question why we haven't done that. Then give the model, limit load, local limit load model, and show some blind element explanation, and then choose the conclusion. Okay, EDF Energy is the UK's largest new electricity generator. So our nuclear power generation part generates about 20% of the electricity to the England, Scotland, and Wales. So we operate 15 reactors with 40 advanced gas-cooled reactors. That's very high temperature, and 1 PWR. This is quite normal as others. So EDF Energy will perform structure integrity assessment to support our power station safe operation and life extension of the plant. So for this reason, we develop and maintain structure assessment procedures. So this one, I believe, is very famous about R6, that's assessment of the integrity of structure, contain defects. Another one is for high temperature assessment procedure for high temperature response of structure. So the limit load I'm talking about relates to procedures. But today, I only talk about R6 and not measure any high temperature stuff. Okay, in R6, fracture assessment, we use failure assessment diagram method, FAD. So this FAD is geometrical based. So in this assessment, we need an assessment curve and to define two parameters, KR and LR. We better look at this. This is a diagram of FAD. So this is FAC, so the failure assessment curve, and this is the cutoff based on material properties. Then in assessment, you need to define two parameters, LR and KR. This KR is the ratio of K, that's stress intensity factor, over material properties, that's fracture toughness. And P means primary stress, and S is due to secondary stress. We must apply a V factor for that primary stress and the secondary stress interaction. So this is providing R6. Another one is LR. This is a load applied, primary load applied, and now by limit load corresponding to that. Okay. You plot LR and KR into this this diagram, and if the inside this region and accepted, if it goes outside, then normally we say that's not accepted. So the margin of assessment is from this point, assessment point, you somehow go to the boundary of this FAC to calculate your margin. But it's not the topic of today. So use this method, which is J-score-based FAD method. But in assessment, you don't need to calculate any J-scores. You only need to know K, elastic parameter, but you need to know limit load. However, behind that, the assessment method, J-score is calculated using the reference trace J-prediction method. It looks like this equation, epsilon ref, sigma ref is a reference trace, and E is your modulus. E is elastic J, calculated from K. Then LR is the same as we just see, divided by LR equals the reference trace over sigma Y. So that's exactly same as this one, just in different way to produce that. Okay. This is another way, for a very general way, to show that the reference trace method behind R6. I'm not going to talk about now, but so now we know the limit load is a very important parameter to affect your fracture assessment. So many people think limit load is about the plastic collapse, but in R6 fracture assessment, limit load is a parameter, firstly, to more accurately and conservatively predict jet growth rather than plastic collapse. So in many references, they talk about that the reference load, not limit load, but I'd rather to use limit load because reference load normally gives you the solutions, but limit load, we have many solutions to use. For limit load used in R6, we have a global limit load or local limit load. The global limit load is a load level corresponding to, load line displacement becomes unbounded. So, but the local limit load is only considered the yielding, but not plastic collapse around the defects. Give examples very easy. This is a plate with surface crack and tension. This is displacement. This is normalized load. We can see global limit load corresponding to the load displacement sharp changing. Okay, it's very easy. Using your FE method, you can very quickly determine that. But local limit load is defined for yielding of the ligament all around this small area. So for this case, it is about there. So you cannot predict that from load displacement curve. It's use local stress trace information. So when in assessment, we need to provide limit load solutions to the users. So for simple geometries, it's quite easy to create global limit load solutions. We have some solutions in R6. But for very complex structures, provide global limit load solutions is almost impossible. Why? So for example, this one, you have a defect could be anywhere. The thickness, diameter could be any of that, combination. Load could be pressure. You could be bending here, in-plane bending, out-plane bending, torsion. So you give the thick handbook like that, give solution, not possible. So for this case, the developed local limit load solution will be a good solution for that. because we only consider stressing information locally at crack location, so without load types. Okay. But for this case, we need electroplated gate growth to validate the method. So aims of this work to develop local limit load model for local limit load calculations used in structure integrity assessment, and also create guidance in R6 section 2.4 for people to use, how to use it. Okay. Now, so we know the limit law and the geometrical relationship now. So next step is very easy. I describe the local limit load model I gave. Okay. My model is like that. If you have a surface crack that's deeper, the depth A and less to C at any location C like here, then you create a plate. This plate with a crack size, rectangular crack surrounding this crack, okay? Then the thickness is the same as the rear structure, but the length is just artificial, so it's quite long, not same as the geometry of the local. Then you need to define the weights. The weights is defined by here based on C, that's crack length. This is very different from other solutions. They use T. And also, weakly related to L over T, that the crack depth, and the K is a geometry factor that can be calibrated and recommended. Okay, then you need to do is elastic stress analysis, unpredictable analysis, to determine stress state at here, the point. So what do you need to do? And the member stress, bending stress, you can check to that. Then you parallel stress, parallel crack, okay? That you have a member stress 2m, sigma 2m, and maybe some shear stress. Then you apply the stresses here to this plate as a load. Then calculate the global limit load of this plate. Now, this global limit load can be used as local limit load here. Okay. This is the full story. Then you ask how to calculate the limit load for this plate. And this without shear stress, we can calculate the reference stress. Here, reference stress and the limit load is the same thing. So for convenience, we represent reference stress. So here, think about AMA is normalized limit load for tension cable. This has been developed and published in this paper. So it's an available solution. So we just use that solution here. If you have a shear stress, then you can correct shear stress to this total. Then use this sigma ref define error law. This error law then can be used in assessment. Okay. This is a full story. So, but not that. This is defined from a global limit load of plate, but it's used as local limit load of the structure. Now, show some finite element validation. So, because our aim is predict J, so we use finite element J result. Then use this local limit load where reference stress to predict J. Now to compare this predicted J with FEJ. So the idea is very simple. Just compare to say if you are conservative, it's how much conservatism is there. I collected about over 273 cases for plate with symmetrical cracks.
Excuse me, Dr.
Okay, that's
I need to remind you, 3 minutes.
And then with biaxial load, then axial defects in cylinders, then some errors. So all from published literature. Then for each case, we calculate the geometrical non-compare. This one is for plate. This is the prediction for the red curve. And this is FE data. So for this case, for pure-tension, pure bending, combined tension bending, all conservative. Right? More cases, biaxial load, you play. And this is for cylinder with axial effect. This cylinder with internal symmetrical crack under pressure. That's the conversion crack. The conversion crack under bending. The conversion crack with bending, but the external crack, bending. Finally, that's the elbows. Elbows for axial defect, and this for the conversion crack. So all gives a very conservative results. Some of them are not very good, very conservative, just because it's the assumption of stress. You only consider maximum stress, and for bending case, the stress does not change a lot. So that's the reason. Okay, now conclusions. First thing, we developed a new local limit law solution to estimate local limit law for use in structural integrity assessment. And this method has been validated to use available FE results, show conservatism, but we still need to do further validation using very complex FE results. So because our aim is to assess complex structure, not a simple plate and pipes. Okay, that's it. Thank you very much for your attention.
Thank you very much. It was really interesting presentation. If you have questions, you can ask it at the end of the session.